Hello and Assalamualaikum everyone. In this video, we're going to move on to lecture 4 on Markovian queuing models involving finite models. Okay, so first up, we're going to look at a single server model with finite queue, or also known as MM1K queue. Okay, first let us consider a single server queue with arrival rate lambda and service rate mu. Okay, so in this type of model, there is a limit of k placed on the number of customer allowed in the system at any times. So only k customers are allowed in the system. Okay, so basically, the approach here is identical to MM1 model, except that there will be no more arrival whenever the state of the system is greater than or equals to k. Okay, so basically it means that only k minus 1 customer, okay, are allowed to wait in the queue. Okay, so your state can only be up until k. Okay, so the arrival rate when your I or your state is greater equals to k is 0. Okay, only k number of customer is allowed in the system. So figure 4.1 basically illustrate the MM1K queuing model. Okay, so you have an arrival rate of lambda, service rate of mu, and the number of customer allowed in the system of k, where k minus 1 customer is allowed to be waiting in the queue. Okay, so previously, we have learned that the traffic intensity rho, okay, which is lambda over c mu. For this case, since your c is equals to 1, okay, so your rho is lambda over mu, okay, must strictly be less than 1 in order for the queue to reach its steady state. Okay, however, okay, for the case of finite queue, the system is allowed a certain number of customer in the queue, hence it will allow the value of rho to be greater than 1 because the number of customer that is allowed to be waiting for service is controlled by this value k over here. Okay, so the value of rho in finite queuing model, okay, is allowed to be greater equals 1. Okay, so basically for MM1K model, okay, so we have our arrival rate lambda I equals to lambda, okay, for I equals to 0, 1 until k minus 1, and equals to 0 for your I greater equals k. For your service rate, mu I is equals to mu for your I equals to 1, 2, until k. Okay, the number of customer allowed in the system. Okay, and then 0 when your I is greater than k. Okay, so by using the prior theory that we developed for our MM1Q, so we will get our probability of being in state I is equals to lambda over mu to the power of I by naught for I equals to 1, 2 until k, and then 0 otherwise. Okay, so next what we're going to do is we're going to determine the value of our pi node. Okay, so for this type of queue, we're going to consider two cases each time we try to derive. So the first case would be rho not equals to 1, and the second case is rho equals to 1. Okay, so basically similar to our MM1Q, we have our pi naught equals to 1 over the summation of I equals to 0 up until k rho to the power of I, okay, where your rho is equals to lambda over mu. So let us consider our first case for rho naught equals to 1. Okay, so for your pi naught, you have 1 over the summation of I equals to 0 until k rho to the power of I. Okay, so which is equals to 1 over 1 minus rho to the power of k plus 1 over 1 minus rho based on the sum of finite geometry series of the summation of k equals to 0 until n minus 1 ar to the power of k is equals to a times 1 minus rn over 1 minus r. Okay, so we can further simplify to get 1 minus rho over 1 minus rho to the power of k plus 1. Okay, so this is for the case of rho not equals to 1. Okay, so for rho equals to 1, we will have pi naught equals to 1 over the summation of I equals to 0 until k 1 to the power of I. Okay, so which will give us the value of 1 over 1 plus k. Okay, based on the sum of I equals to 0 to the power of, I equals to 0 until k for 1 to the power of I is equals to 1 plus k. Okay, so for rho equals to 1, we will get our pi naught equals to 1 plus k. Okay, so thus for mm1kq, we will have our pi I, okay, is equals to 1 minus rho over 1 minus rho to the power of k plus 1, okay, times rho to the power of I for I equals to 0 until k and rho not equals to 1. And for rho equals to 1, we will have 1 over 1 plus k rho to the power of I for I equals to 0 until k for rho equals to 1. Okay, so this is the value of our pi I for MM1K model. So next, we will determine the measure of effectiveness for both case. Okay, so first let us look at the value for L for rho not equals to 1. So your L is equals to the sum for I equals to 0 until k I pi I. Okay, so which when we substitute will give us 1 minus rho over 1 minus rho k plus 1 times I pi rho to the power of I. Okay, so next we're going to take one term of rho out, okay, and all of this term out. Okay, so we will have rho times 1 minus rho 1 minus rho to the power of k plus 1. Okay, then we are left with the summation of I equals to 0 until k for I rho to the power of I minus 1. Okay, So this term here, okay, is actually the derivative for rho to the power of I with respect to rho. Okay, so we're going to simplify the term. Okay, so we're going to rewrite, okay, the front part 1 over rho k plus 1. Okay, and then we're going to differentiate the summation. Okay, rho to the power of I. Okay, so which will give us okay the value of the summation for rho to the power of I for I equals to 0 until k, okay, as we have shown earlier. Okay, 1 minus rho to the power of k plus 1 over 1 minus rho. Okay, so you're going to differentiate this term with respect to rho, okay, which will gives you, sorry, okay, so the same front part, okay, so which will basically gives you a quite long term, okay, so I need you to double check this term, okay, so you should get negative k plus 1 times rho to the power of k over 1 minus rho, okay, plus 1 minus rho k plus 1 times 1 minus rho to the power of negative 2. Okay, so simplifying this, you should get rho times 1 minus k plus 1 rho to the power of k plus k rho to the power of k plus 1 over 1 minus rho k plus 1 times 1 minus rho. Okay, so this is the value for L, okay, for your rho when your rho is not equals to 1. Okay, so next we're going to have a look at the value of L when your rho is equals to 1. Okay, so the summation is the same, I by I. Okay, summation of I equals to 0 until k I, okay, 1 over k plus 1 rho to the power of I. Since your rho is equals to 1, okay, so this terms is actually 1 to the power of I is equals to 1. So we can just substitute it directly with the value of 1. So you are left with I times 1 over k plus 1 only. Okay, so the same goes with the terms here. Okay, so you can just substitute it with 1, so you are left with 1 over 1 plus k for your pi I. Okay, so after that, what we're going to do is we're going to factor out 1 over k plus 1, so we are left with I equals to 0 until k, summation for I, okay, so which is the same as the summation for I equals to 1 until k for I, because when I equals to 0, the value is 0. Okay, so which will gives you, based on the sum, okay, which will gives you 1 over k plus 1, okay, times k plus 1 over Okay, so simplifying this, you should get k over 2. Okay, so this is based on the sum of, okay, so you can check for n equals to 1 k, okay, for x you should get k plus 1 over 2. Okay, so we just substitute the sum. Okay, so simplify, we will get k over 2. So for rho equals to 1, the value of your L is k equals to 2. Okay, so moving on, next what we're going to determine is the value of our LQ. Okay, so the same as before, we're going to consider two cases as well. So the first case is rho naught equals to 1. So our LQ should be the summation for I equals to 1 until k. Okay, so I minus 1 pi I. Okay, and we're going to use, okay, the value of LQ from our MM1Q, where it is equals to L minus 1 minus pi naught. Okay, so we just substitute the value of pi naught for rho naught equals to 1. So we should get L minus 1 minus rho over 1 minus rho k plus 1. Okay, so you can choose to leave it as is, or you can try to simplify so that we get L minus rho times 1 minus rho to the power of k over 1 minus rho k plus 1. So this is the value for LQ when your rho is not equals to 1. Okay, so for your rho equals to 1, okay, so your LQ, we're going to use L minus 1 minus pi naught as well. So your L for rho equals to 1 is k over 2. Okay, so minus 1 minus your pi naught for rho equals to 1 is 1 over 1 plus k. Okay, so which should gives you k minus 1 over 2 times 1 plus k. Okay, so please check, okay, the simplification whether you can get the same value or not. Okay, so that is it for the value of LQ. Okay, in order for us to determine the value of W, okay, and our WQ, we need to do some adjustment to our Little's formula before we can use it directly. Okay, so we need to consider the fraction of the customer that cannot enter the system, kind of similar to our lambda bar, okay, that we have learned before. But for this particular model, we're going to denote it as lambda efficient or lambda prime, where we're going to consider the fraction of customer that cannot join the system because the system is at its full capacity. Okay, so basically the effective arrival rate or lambda efficient or our lambda prime is equals to lambda times 1 minus pi k. Okay, so then we can modify our Little's formula in order for us to determine the value of W and WQ. So for our W, we will get L over lambda efficient, and for our WQ, we will get LQ over our lambda efficient for both case of rho equals to 1 and rho not equals to 1. Okay, remember for a finite models or finite queue, single server queuing models, you need to consider the case or arrival rate, okay, where we need to exclude the fraction of customer that cannot join the system when the system is at its full capacity, when the system is in state, k. So your lambda will be substituted with lambda efficient or lambda prime, where the value is calculated as lambda times 1 minus pi k, or probability being in state k. Then only you can calculate the value of your W and WQ by using the previously found L and LQ. Okay, so let us take a look at one example. Okay, so consider a small petrol filling station that has one pump only and two further waiting space for vehicles. So vehicles arrive at a random Poisson process and the service times are exponentially distributed. So if the number of vehicles at the station is used to represent the state of the system, we need to illustrate the transition diagram for the system and give its rate metric. So first, okay, so we're going to define our queuing model. So we have only one pump that will represent our server, which is our C, and two further waiting space. Okay, so basically the value of K, or your customer allowed in the system, is 1 plus 2, which is 3. Okay, so this problem, okay, represents MM13 model. So K here is number of customer allowed in the system. Okay, so basically the number of server plus the number of customer allowed to wait. Okay, so you have one server, which is one pump. Okay, so this is MM13 queuing model. Okay, so the state, okay, you can only have state 0, 1, 2, and 3. So any customer that arrive when the system is in state 3, there are no more waiting space. So the customer, okay, is assumed to have leave without even entering. Okay, so let us draw our transition diagram. So you have state 0, state 1, state 2, and state 3. Okay, so your arrival rate, okay, you can denote it as lambda, and your service rate, you can denote it as mu. Okay, so this is general case where you are not given the specific value of lambda and mu. So next, what you're going to do is you're going to write down the rate matrix Q. So you have for state here. Okay, so fill up your rate matrix, okay, as what we have learned during the beginning of lecture 3. Okay, so negative lambda plus mu, this is mu, and then 0, so 0 lambda, negative lambda plus mu, and then mu. So finally we have 0, 0, lambda, and negative mu. So this is your rate matrix. Okay, so next question B, in a steady state condition, we want to find the probability that there are n vehicles at the station. So n will represent your state. Okay, so what you have to do here is you have to use, okay, your steady state equation based on your rate matrix, okay, to determine the value of pi n. Okay, so when your n is equals to 0, 1, 2, and 3. Okay, so try and attempt, okay, and find your pi n, okay, based on the rate matrix. Okay, and that is all for MM1K queuing model.